Hi, welcome back to Pacifica Science. If you check out the board behind me, we're talking in week 4 here about energy. We've kind of given a high-level overview of where all these atoms and molecules come from, all the way from the beginning of our universe almost 14 billion years ago to the periodic table and the 100 plus elements that get together to make the molecules of life. Really, there's actually only a handful of atoms that really get together to make the molecules that we'll be studying in this class. We've already talked about a couple of them today. The notes behind me are for first, second, and third period to get down today, and for fourth and sixth period, this will be the class tomorrow. So this is kind of a preview of the class tomorrow if you're in fourth and sixth period. And in energy is a key concept when you're talking about life. It makes sense when you think about it because life is all about transferring energy from one place to another, from one animal to another, from plants to animals. And the idea of energy that we want to focus on this week that's incredibly important in biology and in physics is the conservation laws. Quick, easy example. You see this type of example all the time with physics teachers talking about the conservation of energy. We'll start with that and then we'll move over to the conservation of matter. But let me grab something here. This is a pendulum I've hung in the classroom. Now we've seen pendulums before, so I wanted to use an example that was familiar. And you know that if you let a pendulum go, it swings out and comes back. And the classic physics experiment that you see as a physics professor, he or she will stand there with a very heavy weight like a bowling ball on a pendulum. And if they stand very still and they're very careful about not giving it a push, occasionally on YouTube and places like that, you'll see physics fails where they actually accidentally give it a push. Obviously, you don't want to do that. If I don't add any energy to this basketball as it falls, it's going to swing out, it's going to come back, but I don't have to worry about it hitting me as long as I'm very careful about just letting it go. So if I let it out, I know that as it swings out and then it comes back, in basketball and the rope here, this one loses a lot of energy very quickly. It's not going to swing higher than when I let it go because you can't get more energy out of a system than you put into it. Life would be really, really weird if I could let a basketball go and it swung out, and all of a sudden it swung back really hard and it came up really, really high like that. My assistant off screen. If you check out the basketball example, that's an example about how the amount of energy in a system can be transferred between types, but you can never get more out of a system than you put into it. You might have heard this, and I'll talk a little bit about it in class, perpetual motion machines. Every once in a while you hear about someone who claims to have invented a machine that can just keep itself going forever. I'm afraid that's not possible. According to the laws of physics, things will always lose energy and run down because they're always transferring their energy to friction, to heat. You're always losing energy in a system. Another really important one is the conservation of matter. A quick example of that, I can just do that with, say, a piece of paper, and I'm just going to use this little bowl. And a lot of times if you do something like this, a simple chemical reaction, burning a piece of paper, this bowl is sitting on top of a scale. And if I burn this paper, and I let it sit here in the bowl, we've all been at campfires, we've all been at barbecues, and you see something like this and you start off with maybe big blocks of wood, it starts burning, and at the end of the night, at the end of the barbecue, you're just left with ashes or the burnt out coals. It seems like there's less stuff than you began with. And yes, technically there is, but the matter that's there. In other words, I've burned some paper now, and there's just a couple ashes left in here. I have it sitting on a scale. Now, I don't have the scale on right now, but if I were to let something bigger than paper burn in here, I would slowly see the weight go down. This might give some people the impression that, well, that matter just went away. It's gone. But I want you to think about this. In a system, again, a system is just a closed container. Coke bottle, right? We've all seen Coke bottles before. If you were to burn something within the Coke bottle, if I had that paper in a closed system, it would burn inside here. It might turn to ash. But then when it was done, if it was totally sealed up, used up the oxygen that was in the bottle to burn, if it was totally sealed up, it wouldn't have lost any weight. In other words, the mass of this bottle, if it was sitting on a scale, like this bowl is sitting on a scale right here, it would stay the exact same weight. The conservation of matter tells us that matter can change forms. In other words, it can, the water molecule that we drew this week up on the board several times, or last week on the board and today's on the board, you can switch around water molecules. You can get the oxygen pulled away from the hydrogens. They can recombine, but you never can get more out of a system than you put into it. You always end up with the exact same amount. The gentleman that I had mentioned earlier in the year, Richard Feynman, explained it like this, and this is an explanation that you might have heard earlier, but he was talking about, think about a play school, like an elementary school where you have a lot of blocks, and the kids are playing with blocks. And at the beginning of the day, you've got a bunch of blocks that have the letters of the alphabet, 26 blocks. So long as none of those blocks go out the window or get lost or go home with one of the children that was in the preschool, at the end of the day, yeah, they might be lost somewhere. They might be in a cabinet or under a carpet or somewhere around that room. But so long as none left the room, you will always, at the end of the day, still have 26 blocks. His example was, imagine they're perfect blocks. Well, the blocks, of course, represent atoms. And in chemistry, the number of atoms that you start with in a chemical reaction is always the same as the number of atoms you end with in a chemical reaction. These conservation laws are really, really important in science because when we do experiments, at the beginning of a chemical reaction, at the beginning of an experiment that has energy involved in it, when you take an accounting, when you add up everything at the very end, it should be exactly equal to what you began with. And if it's not, hey, that tells you that you're missing something. It tells you that there's an opportunity to learn what's really going on. On the left here, we see our notes from today. And on the right side, we see a shot from Walter Lewin. He's an MIT professor, since retired, but he does this great experiment. And you can catch it on YouTube where he lets it looks like a small bowling ball swing on a cable. It goes way out, comes right back. You could have some pretty good nerves of steel to stand there while it comes swinging back at you, but it's a great demonstration of the conservation of energy. He knows that as long as he doesn't add any energy to that pendulum, it's not going to come back and knock his glasses off. In other words, it's not going to swing higher than it did when he let it go. And on the next page of our notes today, we had a simple energy transfer example. In other words, electromagnetic radiation, light from our sun, reaching Earth, photosynthesis, a chemical reaction, using the energy from the sun to take carbon dioxide and water, change it into glucose and oxygen, the classic. On the right side, you see the picture that's in our books, page 118, that I asked you to copy into your notes today. And here is your challenge. It's a tough challenge, but let's throw it on out there. What's wrong with that picture? In other words, it's just about right. It's carbon dioxide plus water makes glucose and oxygen. It is not exactly wrong, but it's definitely incomplete. Think about it for just a second, and let's get to the answer on the next slide. And here you go with the answer to that one. Now, this is a pretty advanced question. It's not going to be on any test, at least not yet. But if you check out the answer to the question, the first one there, CO2 plus H2O yields or makes, that's what the little arrow means, sugar, glucose, C6H12O6 plus O2. That's right, that is photosynthesis. But if you look at the one that's written in green down at the bottom, it's got little numbers in front that show that actually you take 6 molecules of carbon dioxide, 6 molecules of oxygen, you make 1 molecule of sugar or glucose, and 6 molecules of oxygen. In other words, what we're doing at the bottom there is we're making sure that you've got the same number and type of atoms on each side of the chemical equation. The first one is correct, but it shows us magically creating some atoms, and that just doesn't happen in nature. According to the law of conservation, you've got to have the same number of atoms as going into a reaction as you have on the other side of the reaction when you're done with everything. They might have rearranged, it might look different, but you have to have the same number and type on each side. All right, we'll pick this up next week. Have a great Tuesday, everybody, and talk to you soon. Bye-bye.